So suppose we have a random variable, let's call it x, and we know that x follows a normal distribution. We don't know the mean of x. We're going to call that mu. And suppose that we know that the standard deviation is 1. So x is distributed normal, mu 1. We want to take a sample of x, say that x sample is 4, and then it turned out to be 6. We want to use this sample to estimate mu here. And we're going to use the method of maximum likelihood. First, just intuitively, what would you guess is the mean of x, or the expectation of x, given this sample? Our best guess would probably be that the expectation of x, mu, it's the sample mean. That's going to be our best guess for mu. You can't do better than that guess. And we're going to write a proof of this. So the method of maximum likelihood works like this. We say, what's the likelihood of seeing this sample? We're thinking about the PDF of the normal distribution. We combine it with d norm. The density, seeing 4, given a specific mu, times the density of seeing 6, given specific mu. This is the likelihood of the sample. And then we're going to choose mu in order to maximize this likelihood. Choose mu to maximize likelihood. So what's the density of the normal distribution? We have an equation for that. The PDF, normal distribution, is 1 over the square root 2 pi. And it's supposed to be sigma squared here, but we said our standard deviation is 1. So I'm just going to not write the sigma squared. And then exponential function, so e to the x minus mu squared in the numerator divided by 2, and it's multiplied by sigma squared, but our sigma squared is 1. So that's the density of the normal distribution. And we're going to say, what is f evaluated at 4 times f evaluated at 6? And then we're going to think about how we could choose mu to maximize that likelihood. Evaluated at 4 goes like this. 1 over root 2 pi times x 4 minus mu squared over negative 2 times 1 over root 2 pi x 6 minus mu squared over negative 2. I can simplify this a little bit. I have these two things multiplied. In the denominator here, I'll have root 2 pi times root 2 pi. So that'll just come out to be 1 over 2 pi. And then here I have the e to the a times e to the b. That's equal to e to the a plus b. Twist down a little bit. I can also write this as x. It'll be 4 minus mu squared plus 6 minus mu squared over negative 2. The trick is, before I introduce that, this is the likelihood of seeing the sample for 6. And then we want to choose mu. Mu shows up here and here. The idea is we want to choose mu to maximize this thing. The way we would do that is to take first order conditions, find the partial derivative of this likelihood with respect to mu, and set that equal to 0. Find the maximum. It looks like this. Then at the maximum, the derivative will be 0. That's the idea. The thing is, finding the derivative of this is a little more complicated than it needs to be. So I'm going to use the trick that I mentioned earlier. I'm going to take the log of this thing, log likelihood, and log is a strictly monotonic transformation. So the maximum of the log likelihood will be the same as the maximum of the likelihood. So maximum of the log likelihood lets us get rid of that exponential function and make our computations easier. So what is the log likelihood? It is log 1 over 2 pi plus the log of the exponential function of this, which just simplifies to being this nice. So I'll just write 4 minus mu squared over negative 2 plus 6 minus mu squared over negative 2. I'm going to take the derivative of this, and now it's the derivative of the log likelihood function with respect to mu, and then I'm going to set it equal to 0. So let's take the derivative. This part doesn't have a mu in it, so that just goes to 0. So let's use power rule and a chain rule here. This few goes out to the front for the power rule. I get 2, 4 minus mu, and decrement the exponent by 1. With the chain rule, mu is multiplied by a -1, so that -1 comes out here, divided by a -2. Same thing for this term, 2, 6 minus mu to the 1 times -1 over -2. The 2's cancel here. I'm multiplying by a negative and then multiplying by a negative again, so that would cancel out. So what I'm left with is just 4 minus mu plus 6 minus mu. I took the partial derivative with respect to mu, and then I'm going to set it equal to 0. Simplifying a little bit more, I get 10 is 2 mu, or mu is 5. Whoa, what did we do here? We said, what is the value of mu that maximizes the log likelihood of seeing the data of 4 and 6? Our guess was that x had an expectation of 5 because that's the sample mean, and then we proved it mathematically. Hopefully that was clear.